My name is Cole Brower, and I am a PhD student with the IDEA Lab at Arizona State University. Our work focuses on developing low cost robotics for education, and in particular, we focus on laminate robotics and 3D printing. In this presentation, I'll be discussing our work on a voxel-based CAD framework for helping to plan functionally graded models and multi-step fabrication processes. Multi-material fabrication is an approach to creating parts that are made up of multiple materials and are made with multiple manufacturing processes. This provides opportunities for creating single parts which can take the place of entire assemblies made using conventional techniques. For example, the images on the right show a robotic finger with integrated grips and joints, and a robot frame with integrated electronics and motors. These techniques are ideal for creating durable, low-cost robots. They have the benefits of compliant devices, such as integrated flexible joints or reduced part count, but they also expand upon these capabilities by allowing for features such as reinforcement using materials with different properties or integrated electronics. They are also accessible through different combinations of low-cost prototyping methods, making them good for environments where cost or iteration speed are important. However, multi-material fabrication faces several challenges. Currently, it is not well supported by CAD tools. Many current CAD tools only deal with the surface geometry of a part and are limited to specifying materials per body, not within parts. Graded materials in particular are hard to model with current CAD tools, and these have many uses in robotics for creating material transitions or controlling the stiffness or center of mass of a part. In addition, modifying parts with multi-material features and planning the processes used to create them must be done manually. This not only includes developing the process steps, but also generating features such as support structures, molds, or fixtures. Creating these features often requires specialized knowledge of the tools used, presenting an additional barrier to the use of multi-material structures. The goal of our work is to address these challenges by developing a framework and software tool for representing and manipulating 3D objects with material data, for automatically creating required support features, for generating the process steps needed for manufacturing a part, and generating the files needed by this process, such as the G-code files for different machines. Contributions in this area by previous work include mathematical approaches to performing solid geometry operations on multi-material parts, computer representations of multi-material parts, including voxels, surfaces with gradients, and finite element meshes, process planning algorithms for specific processes, and software packages to perform these tasks for specific processes, such as G-code generators for CNC mills or slicing software for various 3D printers. Our work seeks to combine these elements into a single, easy-to-use software package for creating parts that span multiple materials and process types. As a starting point for this framework, we selected a voxel-based model representation. Voxels allow for conceptually simple geometric operations and correspond well to layer-based processes. We selected a representation where each voxel stores a Boolean value indicating the presence or absence of the material, which allows for fast geometry operations, floating point values representing the percentages of materials present, similar to how different color channels are present in a color image, and a null material channel that can be used to represent density. These values are constrained such that the Boolean value is always 0 or 1, and the sum of all the material channels, including the null material, will always equal 100%. Based on this representation, we defined a series of solid geometry operations. In this figure, the top row shows union, difference, and intersection operations. These use a material priority approach to handling multi-material models. These can also be combined to form other logical operators. On the bottom row, we have material-wise addition and subtraction. These allow for computation on materials. For example, in the subtraction, we're starting from a mixture of materials that results in purple, subtracting out the red material, giving a blue material. This provides opportunities for computing mixed transition materials. We also have created dilate and erode morphology operations, which can also be used to perform opening and closing algorithms. We have also defined a blurring operation to allow for material interface modification. This figure shows Gaussian blurring applied to a 3-material model, and Gaussian blurring applied to a region of a 3-material model. After applying these operations, several cleanup steps are required before generating final files to ensure that results have a physical meaning. The first step is removing negative materials. This can result from running the subtraction operation and has no physical meaning. The second is updating the Boolean values. These values may be out of date following operations that result in voxels with material channels that only contain negative values or zeros. After applying these steps, some voxels may contain material channels which do not add up to 100%. To correct this, two approaches can be used. The first is to maintain the ratio of the materials present and simply scale them up to fill the voxel. The second is to leave the voxels at their current densities and scale the null material value to account for the remaining material. This figure illustrates a purple cylinder which has had a red cylinder subtracted from it, resulting in a portion of the model that contains only blue material at 50% density. The two options on the right show the results of either maintaining the ratios of materials or maintaining the densities of materials present in these blue voxels. Using these operations, we can define features helpful for planning manufacturing processes. These features are affected by process constraints, such as the ability of a process to control cutting depth, the tool head size, or the length, curve, or orientation of the tool head. As such, variations must be defined for different processes. To illustrate these features, I will be using this example part. This part illustrates a center cavity and overhangs. I will be assuming that material removal or deposition occurs in the vertical axis. These figures illustrate the manufacturing features that we have defined. Keep out represents material which the process may not modify. For a laser, this is material that it cannot access because of its lack of depth control. For milling, this represents material underneath overhangs. Additive manufacturing will not have keep out. Clearance represents material that is affected by the process acting on a part. For example, a milled part can have another part underneath it, but a laser cannot because the laser will affect the part below the cutting area. 3D printing will have a similar clearance to a laser. Web represents supporting material surrounding a part, and it is defined for a given removal process. Web for removal by a laser process must be completely outside of the boundaries of the part. Web for removal by milling can overhang the part. Web is not defined for 3D printing since it is an additive process. Support represents regions around a model where support material may be added to connect it to the web. This is again defined by the process used to remove the supports. User support is the intersection of this with a user-designed support structure. Using the above operations and features, we can define a number of manufacturing process algorithms. We can perform modifications to a model, such as adding clearances around inserted parts or generating material interfaces. We can generate support features, such as fixtures and molds. And we can prepare and export the required files for different processes, such as 3D models, G-code, or images. Next, I will show two simple examples of part modification algorithms for different part classes. First is creating a 3D printed model with a blurred region. The steps for processing this model are modifying the material boundaries with a blur, reducing the number of materials present and separating distinct materials so that a model can be exported for each material. To produce this part, these models could then be loaded into a multi-material 3D printer's software. Material properties could be assigned to each file, and the part could be printed. These figures show the input and output from running this process on the example model, and the definition of the algorithm used. This result could be created using a PolyJet printer. The second example is taking a 3D part and embedding an electronic component in it. To process this model, clearances must first be added around the embedded part. A path for inserting the part must be considered. A model must be exported containing only the printed components, and then the G-code for this model has to be generated with pauses at the correct layers for performing the insertion steps. To produce this model, this G-code would be loaded onto a 3D printer, the printing would be started, and when it automatically pauses, the part would be inserted, the printing would then be resumed, printing over the part and sealing it in. This would be repeated as many times as needed if there are multiple embedded components. This figure shows the result of running these steps on the input model. Notice that there's clearance around the motor shaft, a path above the motor shaft to a single layer where the pause can occur. There is also a path above the wire channel on the back of the model. As defined here, this algorithm only accounts for a simple clearance path to a pause layer. If desired, it could be easily adapted to capture the material removed above a part and have it print separately as a shape adapter. To demonstrate our framework, we created a Python implementation and used it to process the second example. This figure illustrates our workflow. First, the user designs their intended model in a 3D modeling program. In this case, we are using a voxel modeling program for simplicity. These files are then imported into our framework, where the required modifications are performed, a list of the required G-code modifications is stored, and the STL file is exported. This STL file is sliced with a slicer specific to a 3D printer, and the resulting G-code file is brought back into our framework, allowing the modifications to be made. Finally, this G-code file is sent to the printer. Our Python implementation is built around classes for voxel and mesh data and includes functions and class methods for performing the operations described previously. The figure on the right shows a simple example of using our framework to apply a blur to a model. Using our Python implementation, we built a script to perform the algorithm described for generating clearances on an embedded part. We then applied this algorithm to a second model of the same class, showing how a single script can easily be used to process multiple models. The resulting files were used to produce these parts using an FDM 3D printer. These figures show the results and illustrate that the part was successfully constructed and assembled. In this case, two material colors were used to highlight the pause layer and do not represent a change in material properties. To process the previous example, our library currently requires between 5 and 9 seconds. This is for a fairly low resolution model with 1 mm voxels. For a more complex example, with 10 times the resolution, STL import, and the application of blurring and support generation algorithms, our library takes between 3 minutes and 6 minutes. These time requirements are acceptable for the classes of models we are currently working with, but we intend to optimize the library further in the future to allow for processing of larger models. These results from testing our implementation showed that the components could be manufactured and functioned as intended, that the implemented processing algorithms were successfully able to be reused within their respective classes of components, and that the implementation was scalable to higher resolution models. In conclusion, our framework was effective at processing models and producing files needed for manufacturing. Our examples demonstrate that the framework can successfully produce models that would traditionally be difficult to design. Future work with this project could include automatic selection of process steps, automatic process validation, generation of user-readable instructions, the development of a graphical user interface, and further optimization of processing time. More information on this project can be found in our paper, Voxel-Based CAD Framework for Planning Functionally Graded and Multi-Step Rapid Fabrication Processes, available through the ASME Digital Collection. The framework library and example scripts are available on the Voxel Fuse GitHub repository. This work was supported through the FURI program at ASU.